All right. So for those looking for a streaming ABR talk, consider this your distraction. But I do hope you guys will walk away with a few things on L4S, or maybe one thing. Yeah. All right. Just going to introduce L4S. By the way, the timer is not? Okay. All right. Okay. Understood. Now I'm rocking and rolling. I'll introduce you to L4S. We'll talk about speed test for L4S. We'll talk about what has been done so far on speed test for L4S and what we're proposing, and then we'll share some results. What is L4S? Just a brief primer. Essentially, there are two queues now at a service provider. Think of the access network. So these two queues basically alleviate the problem of head-of-line blocking that occurs for low latency traffic behind conventional traffic, especially progressive download traffic. So, however, on the other hand, low latency traffic itself has become quite capacity seeking. Why? Because it's not just audio, it's also cloud gaming, it's video conferencing, so on and so forth. So in this talk, we'll definitely cover more about the mechanisms that are used. But at the high level, there are two queues, the low latency or the L queue, the default or the classic traffic queue. There are mechanisms that we'll talk about that ensure that low latency traffic actually gets priority, but not in bandwidth. So essentially, it gets priority in latency, but not in bandwidth. And we'll talk about what that really means. Every statement is actually always qualified, right? So, yes, ISPs are supporting this technology. Comcast, T-Mobile have come out very publicly in favor of L4S and actually deploying L4S. And yes, there are a couple other things related we won't talk about much, such as queue protection, which basically allows for L4S to boot out application packets that try to abuse it. So two important concepts. One is the scheduler wait. So essentially, there is a round-robin scheduler that is operating across these two queues, and it is picking up packets from either the low-latency queue or the classic queue. However, there is a certain share of the low-latency queue that is limited. This is to really prevent starvation of the regular traffic, the classic queue traffic, but this share, this proportion of transmission opportunities is not to be treated as a hard partition. So if there were no traffic that was low latency, then the classic queue can take up all of the capacity of the customer's provisioned bandwidth. If there were no classic traffic, then the low latency traffic can actually take up all of that bandwidth. It is essentially only when both traffics are trying to push on each other that this hard partition becomes sort of the quiescent operating point in which your bandwidth is divided. Whatever was provisioned, if you were given 200 megabits per second, then that will be provisioned in this share proportion. The second thing is the coupling weight. So the magic of L4S is basically using TCP Prague. So TCP Prague basically uses ECN in a certain way, the explicit congestion notification that exists inside of the toss byte of your IP header. So what it really does is it relates, so there's one queue in which the congestion control mechanism is a packet drop, whatever you're using, Red, Codel, whatever, right? In the other one, the congestion control mechanism is a congestion experienced packet marking, right? And so in one case, you are certainly using brute force, and therefore you see that sawtooth that occurs with classic. But in the other case, you are actually giving fine-grained feedback back to the sender through the congestion experienced bit to tell the sender that, hey, you can reduce your throughput a little bit, hey, you can increase it a little bit, and that comes through as the proportion of total packets which actually have the CE mark inside of them, right? But the beauty of TCP Prague comes from essentially the idea that these two things are related. And what that leads to is back pressure. So we talked about how essentially the classic queue cannot be starved, But the second thing about this is that that back pressure pushes on. So if the drop probability increases in the classic queue, it pushes on the low latency queue. Here's an example of what that happens. Essentially, there, like I said, the coupling mechanism has two aspects, one of which is intrinsic to the low latency queue, that's the prob native value, the other of which is a result of the classic queue. Essentially, if the classic queue is starting to push on the low latency queue, then the low latency queue reduces its capacity. So this is an example of a speed test for L4S that we can do today, the Excentis byte blower. So it's at an end device. And at an end device, you basically choose L4S in a sort of a drop-down menu, and you kind of choose, do I want to run this speed test for L4S, or do I want to run this for Classic? And so with that drop-down menu, you basically run your speed test. You can get some advanced metrics. All that is fun, and it is actually needed. But what about whole home speed tests, like the way we know them? Like, I mean, are there any benefits that are to be derived by the consumer and the service provider in running whole home tests? So through this work, what we want to show is that we have developed what is essentially an enhanced, what you might call a coexistence-aware speed test. What it detects is whether latency-sensitive traffic is protected under load, whether bulk traffic is fairly throttled rather than starved, bulk traffic is the classic queue traffic, and whether the AQMs and the schedulers are functioning as intended. So essentially, from the service provider standpoint, it'd be interesting to know, is my queue management quality good or not good? Is there buffer bloat or not, right? Is the scheduling weight parameter configured correctly or not? From a service provider standpoint, it'd be interesting to know, because all that the service provider knows today is, hey, I have low latency. What does that really mean, right? So from the service provider standpoint, it'd be interesting to educate them. It'll help them understand that L4S can take all of your capacity, Classic can take all of your capacity if they're operating independently, but there is one operating point that does get respected when you are pushing capacity on both service flows. So this is the design of the speed test. Essentially, it's still a greedy TCP transfer, the way we know speed tests to be. But now we open up two different, or in each case, essentially multiple different TCP connections, but two different service flow connections. I'll treat them as one that is L4S and one that is not. And so I'm going to walk you through just that graph at the bottom, the time progression graph, to help explain how this speed test could potentially work. So you start with one. The low latency service flow is actually better to start with, because normally scheduling weight is set to favor the low latency flow. So for faster convergence, more efficient speed test, it's better to start with the low latency flow. You start with the low latency flow, you open a greedy TCP transfer for that low latency flow, you run it for a while, you get your maximum sustained throughput, then you start your classic service flow. Now they are both operating in the coexistence regime, in the concurrently. And at that point in time, basically, and so this is a very idealized flow, we'll see actual experimental results, but the share of first, when you started the low latency flow, it took up all of the provisioned capacity. Then its capacity comes down based on the scheduling weight to the share of the low latency, the share of the transmission opportunity, times the provision data rate, whereas the classic service flow takes 1 minus share times the provision data rate. And then you stop the low latency service flow so that you can also observe what happens with just the classic service flow. And as is normally expected in a healthy system, the classic service flow will take all of the provision data rate after that. Here's some ideas around the user interface. So, for example, the left dial here, just an example, downstream capacity, it kind of shows that when they're not operating at the same time, they both kind of end up taking, let's say, close to 200 megabits per second. But when they're actually operating together, then the right dial kind of shows how that 200 megabits per second kind of gets divided between the low latency service flow and the classic service flow. Another way to look at this, using the bar chart here on the left, and imagine this as an animation would run with speed tests, is in step one, you start off the bulk transfer, and low latency service flow greedily takes up all of the provisioned bandwidth. Step two, you open up the classic service flow, it pushes back on the low latency service flow, and you start seeing where that operating point is, the share L and the 1 minus share L. And then in step three, you turn off the low latency service flow, and the classic throughput then, through its greedy bulk transfer, takes up all of that bandwidth, the provisioned bandwidth. Here's an example of a simulation, and this is what you would expect. So basically, 20 seconds, first 20 seconds, so talking to those two graphs, left and right, the first 20 seconds is L4S only. Then you start observing that coexistence regime. Here you start seeing how that ECN actually prevents the congestion experienced, and the specific algorithm actually avoids the sawtooth and helps L4S adjust in a fine time grain scale its throughput. And then in the next step, it basically turns off, and then you've got the classic service flow. The second diagram is actually the same idea, but in reverse, in the sense that you first start with the classic service flow, and then you move to the low latency service flow. Here's an example of an experiment that we ran. Here, essentially, we were running dual pi square at the Linux router. The L4S congestion control is Prague style. The classic congestion control here is BBR. And essentially the same idea, 20, 40, 60. So first 20, L4S only. Next 20, coexistence. Last 20, only the classic. And as is to be expected, you generally observe that the total pipe remains utilized, your provision bandwidth remains utilized fully. So in conclusion, the scheduler favors the L4S flow, but imposes a ceiling to prevent the classic flow starvation. Classic flow can apply back pressure on L4S as it gets congested. We kind of show that running a speed test configuration that invokes flow coexistence has several benefits and advantages, both for the ISP and the customer education benefit. One is that it measures usable capacity rather than raw capacity. It could expose buffer bloat and queue management quality, tests fairness, starvation resistance, and finally, it reflects whole home usage patterns. Ready to take questions? Okay, no questions?
Let's take one question from Pierce, who happens to be our next speaker as well.
Oh, no, not quite, isn't it? Yeah, I think so. Yeah. Does the competing BBR flow, does that also interpret, do you mark the packets on the other flow as well?
So not in this case. So I believe there are some ECN enabled versions of BBR, but we didn't use them in this case. So we basically used BBR's intrinsic capability of measuring, bandwidth and RTT, right?
I see.
Bandwidth delay problem.
Okay, and the testing methodology you're talking about looks quite like the responsiveness test that's an IETF draft at the moment. I don't know if you know the network quality test it's in Mac OS, being built in for a few years. It's called responsive under working conditions. It's revision 8, and it basically is a sort of test under load type of thing. I wasn't sure if it was related to this. You use this or not, or you.
I was not aware of it. Does it actually test scheduler waiting?
No, so that aspect isn't there. But what it does, it sort of tests a kind of. I think it sort of sends a stream out and makes sure that you're getting a loaded kind of connection to sort of see what the responsiveness is like.
I see. So the interesting thing about my talk is, I was thinking whether I should call it a Jedi mind trick or not. But at the end of the day, we're talking about low latency. But I only talked about throughput because as of right now, actually latency measurement itself is a fairly ill-developed field for low latency, in the sense that, UCLA has said that you should use working latency or, latency under load, but haven't seen a lot more sort of academic or theoretical treatment of that just yet. And it's partly related to how complex the protocols get on the other end. Yeah.
Fair enough. Thank you. Any other questions? No? Thanks, DJ.
Thank you.